हेलो एवरीवन। आज हम क्लास 12 केमिस्ट्री एनसीईआरटी की बुक से यूनिट 2 सॉल्यूशंस का रीडिंग करेंगे। ये एक ऑडियो बुक है रिवीजन पर्पस के लिए। इस वीडियो में किसी भी टाइप का एक्सप्लेनेशन नहीं है। ऑलमोस्ट ऑल प्रोसेसेस इन बॉडी अकर इन सम काइंड ऑफ लिक्विड सॉल्यूशंस। In normal life, we rarely come across pure substances. Most of these are mixtures containing two or more pure substances. Their utility or importance in life depends on their composition. For example, the properties of brass in bracket mixture of copper and zinc are quite different from those of German silver in bracket mixture of copper, zinc and nickel, or bronze in bracket mixture of copper and tin. 1 part per million in bracket ppm of fluoride ions in water prevents tooth decay, while 1.5 ppm causes the tooth to become mottled and high concentrations of fluoride ions can be poisonous. In bracket, for example, sodium fluoride is used in rat poison. Intravenous injections are always dissolved in water containing salts at particular ionic concentration that match with blood plasma concentrations and so on. In this unit, we will consider mostly liquid solutions and their formation. This will be followed by studying the properties of the solutions like vapor pressure and colligative properties. We will begin with types of solutions and then various alternatives in which concentrations of a solute can be expressed in liquid solution. 2.1 Types of solutions. Solutions are homogeneous mixtures of two or more than two components. By homogeneous mixture, we mean that its composition and properties are uniform throughout the mixture. Generally, the component that is present in the largest quantity is known as solvent. Solvent determines the physical state in which solution exists. One or more components present in the solution other than solvent are called solutes. In this unit, we shall consider only binary solutions. In bracket, that is consisting of two components. Here, each component may be solid, liquid or in gaseous state and are summarized in table 2.1. Table 2.1 Types of solutions. Types of solution: gaseous solutions, solute, gas, solvent, gas. Common examples: mixture of oxygen and nitrogen gases. Solute, liquid, solvent, gas. Common examples: chloroform mixed with nitrogen gas. Solute, solid, solvent, gas. Common examples: camphor in nitrogen gas. Type of solution: liquid solutions. Solute, gas, solvent, liquid. Common examples: oxygen dissolved in water. Solute, liquid, solvent, liquid. Common examples: ethanol dissolved in water. Solute, solid, solvent, liquid. Common examples: glucose dissolved in water. Type of solution: solid solutions. Solute, gas, solvent, solid. Common examples: solution of hydrogen in palladium. Solute, liquid, solvent, solid. Common examples: amalgam of mercury with sodium. Solute, solid, solvent, solid. Common examples: copper dissolved in gold. 2.2 Expressing concentration of solutions. Composition of a solution can be described by expressing its concentration. The latter can be expressed either qualitatively or quantitatively. For example, qualitatively we can say that the solution is dilute. In bracket, that is relatively very small quantity of solute. Or it is concentrated, in bracket, that is relatively very large quantity of solute. But in real life, these kinds of description can add to lot of confusion and thus the need for a quantitative description of the solution. There are several ways by which we can describe the concentration of the solution quantitatively. First, mass percentage, in bracket W by W. The mass percentage of a component of a solution is defined as mass percent of a component is equals to mass of the component in the solution upon total mass of the solution into 100. For example, if a solution is described by 10% glucose in water by mass, it means that 10 gram of glucose is dissolved in 90 gram of water, resulting in a 100 gram solution. Concentration described by mass percentage is commonly used in industrial chemical applications. For example, commercial bleaching solution contains 3.62 mass percentage of sodium hypochlorite in water. Second, volume percentage in bracket V by V. The volume percentage is defined as volume percent of a component is equals to volume of the component upon total volume of solution into 100. For example, 10% ethanol solution in water means that 10 ml of ethanol is dissolved in water such that the total volume of the solution is 100 ml. Solutions containing liquids are commonly expressed in this unit. For example, a 35% in bracket V by V solution of ethylene glycol and antifreeze is used in cars for cooling the engine. At this concentration, the antifreeze lowers the freezing point of water to 255.4 Kelvin in bracket minus 17.6 degrees Celsius. Third, mass by volume percentage in bracket W by V. Another unit which is commonly used in medicine and pharmacy is mass by volume percentage. It is the mass of solute dissolved in 100 ml of the solution. Fourth, parts per million. When a solute is present in trace quantities, it is convenient to express concentration in parts per million in bracket ppm and is defined as parts per million is equals to number of parts of the component upon total number of parts of all components of the solution into 10 raised to 6. As in the case of percentage, concentration in parts per million can also be expressed as mass to mass, volume to volume and mass to volume. A liter of seawater in bracket which weighs 1030 gram contains about 6 into 10 raised to minus 3 gram of dissolved oxygen in bracket O2. Such a small concentration is also expressed as 5.8 gram per 10 raised to 6 gram in bracket 5.8 ppm of seawater. The concentration of pollutants in water or atmosphere is often expressed in terms of microgram into meter per liter or ppm. Fifth, mole fraction. Commonly used symbol for mole fraction is X and subscript used on the right hand side of X denotes the component. It is defined as mole fraction of a component is equals to number of moles of the component upon total number of moles of all the components. For example, in a binary mixture, if the number of moles of A and B are Na and Nb respectively, the mole fraction of A will be Xa is equals to Na upon Na plus Nb. For a solution containing I number of components, we have Xi is equals to N1 upon N1 plus N2 plus dot dot plus Ni is equals to N1 upon sigma N1. It can be shown that in a given solution, sum of all the mole fractions is unity. That is, x1 plus x2 plus dot 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 xi is equals to 1. Mole fraction unit is very useful in relating some physical properties of solutions, say vapor pressure with concentration of the solution, and quite useful in describing the calculation involving gas mixtures. Example 2.1. Calculate the mole fraction of ethylene glycol in bracket C2H6O2 in a solution containing 20% of C2H6O2 by mass. Solution. Assume that we have 100 gram of solution in bracket. One can start with any amount of solution because the results obtained will be the same. Solution will contain 20 gram of ethylene glycol and 80 gram of water. Molar mass of C2H6O2 is equals to 12 into 2 plus 1 into 6 plus 16 into 2 is equal to 62 gram per mole. Moles of C2H6O2 is equal to 20 gram upon 62 gram per mole is equal to 0.322 mole. Moles of water is equals to 80 gram upon 18 gram per mole is equals to 4.444 mole. Mole fraction of glycol is equals to moles of C2H6O2 upon moles of C2H6O2 plus moles of H2O is equal to 0.322 mole upon 0.322 mole plus 4.444 mole is equal to 0.068. Similarly, moles of water is equals to 4.444 mole upon 0.322 mole plus 4.444 mole is equals to 0.932. Mole fraction of water can also be calculated as 1 minus 0.068 is equals to 0.932. Sixth, molarity. Molarity in bracket capital M is defined as number of moles of solute dissolved in 1 liter in bracket or 1 cubic decimeter of solution. Molarity is equals to moles of solute upon volume of solution in liter. For example, 0.25 mole per liter in bracket or 0.25 molar solution of NaOH means that 0.25 mole of NaOH has been dissolved in 1 liter in bracket or 1 cubic decimeter. Example 2.2. Calculate the molarity of a solution containing 5 gram of NaOH in 450 ml solution. Solution moles of NaOH is equals to 5 gram upon 4 gram per mole is equals to 0.125 mole. Volume of the solution in liters is equals to 450 ml per 1000 ml per liter. Using equation 2.8, molarity is equals to 0.125 mole into 1000 ml per liter upon 450 ml is equals to 0.278 molar is equals to 0.278 mole per liter is equals to 0.278 mole per cubic decimeter. Seventh, molality. Molality in bracket small m is defined as the number of moles of the solute per kilogram in bracket kg of the solvent and is expressed as molality is equals to moles of solute upon mass of solvent in kg. For example, 1 mole per kg in bracket or 1 molar solution of KCl means that 1 mole in bracket 74.5 gram of KCl is dissolved in 1 kg of water. Each method of expressing concentration of the solutions has its own merits and demerits. Mass percent, ppm, mole fraction and molality are independent of temperature, whereas molarity is a function of temperature. This is because volume depends on temperature and the mass does not. Example 2.3. Calculate molality of 2.5 gram of ethanoic acid in bracket CH3COOH in 75 gram of benzene. Solution: molar mass of C2H4O2 is equals to 12 into 2 plus 1 into 4 plus 16 into 2 is equals to 60 gram per mole. Moles of C2H4O2 is equals to 2.5 gram upon 60 gram per mole is equals to 0.0417 mole. Mass of benzene in kg is equals to 75 gram upon 1000 gram per kg is equals to 75 into 10 raised to minus 3 kg. Molality of C2H4O2 is equals to moles of C2H4O2 upon kg of benzene is equals to 0.0417 mole into 1000 gram per kg upon 75 gram is equals to 0.556 mole per kg. 2.3 Solubility. Solubility of a substance is its maximum amount that can be dissolved in a specified amount of solvent at a specified temperature. It depends upon the nature of solute and solvent as well as temperature and pressure. Let us consider the effect of these factors in solution of a solid or a gas in a liquid. Two point 3.1 Solubility of a solid in a liquid. Every solid does not dissolve in a given liquid. While sodium chloride and sugar dissolve readily in water, naphthalene and anthracene do not. On the other hand, naphthalene and anthracene dissolve readily in benzene, but sodium chloride and sugar do not. It is observed that polar solutes dissolve in polar solvents and non-polar solutes in non-polar solvents. In general, a solute dissolves in a solvent if the intermolecular interactions are similar in the two, or we may say like dissolves like. When a solid solute is added to the solvent, some solute dissolves and its concentration increases in the solution. This process is known as dissolution. Some solute particles in solution collide with the solid solute particles and get separated out of solution. This process is known as crystallization. A stage is reached when the two processes occur at the same rate. Under such conditions, number of solute particles going into solution will be equal to the solute particles separating out and a state of dynamic equilibrium is reached. Solute plus solvent gives solution. At this stage, the concentration of solute in solution will remain constant under the given conditions, that is temperature and pressure. Similar process is followed when gases are dissolved in liquid solvents. Such a solution in which no more solute can be dissolved at the same temperature and pressure is called a saturated solution. An unsaturated solution is one in which more solute can be dissolved at the same temperature. The solution which is in dynamic equilibrium with undissolved solute is a saturated solution and contains the maximum amount of solute dissolved in a given amount of solvent. Thus, the concentration of solute in such a solution is its solubility. Earlier, we have observed that solubility of one substance into another depends on the nature of the substances. In addition to these variables, two other parameters, that is temperature and pressure, also control this phenomenon. Effect of temperature. The solubility of a solid in a liquid is significantly affected by temperature changes. Consider the equilibrium represented by equation 2.10. This being dynamic equilibrium must follow Le Chatelier's principle. In general, if in a nearly saturated solution, the dissolution process is endothermic, in bracket delta solution H greater than 0. The solubility should increase with rise in temperature, and if it's exothermic, in bracket del solution H less than 0, the solubility should decrease. These trends are also observed experimentally. Effect of pressure. Pressure does not have any significant effect on solubility of solids in liquids. It is so because solids and liquids are highly incompressible and practically remain unaffected by changes in pressure. 2.3.2 Solubility of a gas in a liquid. Many gases dissolve in water. Oxygen dissolves only to a small extent in water. It is this dissolved oxygen which sustains all aquatic life. On the other hand, hydrogen chloride gas, HCl, is highly soluble in water. Solubility of gases in liquids is greatly affected by pressure and temperature. The solubility of gases increase with increase of pressure. For solution of gases in a solvent, consider a system as shown in figure 2.1a. The lower part is solution and the upper part is gaseous system at pressure P and temperature T. Assume this system to be in a state of dynamic equilibrium. That is, under these conditions, rate of gaseous particles entering and leaving the solution phase is the same. Now increase the pressure over the solution phase by compressing the gas to a smaller volume. In bracket figure 2.1b. This will increase the number of gaseous particles per unit volume over the solution and also the rate at which the gaseous particles are striking the surface of solutions to enter it. The solubility of the gas will increase until a new equilibrium is reached, resulting in an increase in the pressure of a gas above the solution and thus its solubility increases. Henry was the first to give a quantitative relation between pressure and solubility of a gas in a solvent, which is known as Henry's law. The law states that at constant temperature, the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas present above the surface of liquid or solution. Dalton, a contemporary of Henry, also concluded independently that the solubility of a gas in a liquid solution is a function of partial pressure of the gas. If we use the mole fraction of a gas in the solution as a measure of its solubility, then it can be said that the mole fraction of gas in a solution is proportional to the partial pressure of the gas over the solution. The most commonly used form of Henry's law states that the partial pressure of the gas in vapor phase is proportional to the mole fraction of the gas in the solution and is expressed as P is equals to Kh into X. Here Kh is the Henry's law constant. If we draw a graph between partial pressure of the gas versus mole fraction of the gas in solution, then we should get a plot of the type as shown in figure 2.2. Different gases have different Henry constant values at the same temperature. In bracket table 2.2. This suggests that Kh is a function of the nature of the gas. It is obvious from equation 2.11 that higher the value of Kh at a given pressure, the lower is the solubility of the gas in the liquid. It can be seen from table 2.2 that Henry constant values for both N2 and O2 increase with increase of temperature, indicating that the solubility of gases increases with decrease of temperature. It is due to this reason that aquatic species are more comfortable in cold waters rather than in warm waters. Example 2.4. If N2 gas is bubbled through water at 293 Kelvin, how many millimoles of N2 gas would dissolve in 1 liter of water? Assume that N2 exerts a partial pressure of 0.987 bar. Given that Henry's law constant for N2 at 293 Kelvin is 76.48 K bar. Solution. The solubility of gas is related to the mole fraction in aqueous solution. The mole fraction of the gas in the solution is calculated by applying Henry's law. Thus, mole fraction of nitrogen is equals to P in bracket nitrogen upon Henry constant is equals to 0.987 bar upon 76,480 bar is equals to 1.29 into 10 raised to minus 5. As 1 liter of water contains 55.5 mole of it, therefore, if N represents number of moles of N2 in solution, moles of nitrogen is equals to N mole upon N mole plus 55.5 mole is equals to N upon 55.5 is equals to 1.29 into 10 raised to minus 5. in bracket n in denominator is neglected as it is very less than 55.5. Thus n is equals to 1.29 into 10 raised to minus 5 into 55.5 mole is equals to 7.16 into 10 raised to minus 4 mole is equals to 7.16 into 10 raised to minus 4 mole into 1000 m mole upon 1 mole is equals to 0.716 m mole. Henry's law finds several applications in industry and explains some biological phenomena. Notable among these are: to increase the solubility of CO2 in soft drinks and soda water, the bottle is sealed under high pressure. Scuba divers must cope up with high concentration of dissolved gases while breathing air at high pressure underwater. Increased pressure increases the solubility of atmospheric gases in blood. When the divers come towards surface, the pressure gradually decreases. This releases the dissolved gases and leads to the formation of bubbles of nitrogen in the blood. This blocks capillaries and creates a medical condition known as bends, which are painful and dangerous to life. To avoid bends, as well as the toxic effects of high concentrations of nitrogen in the blood, the tanks used by scuba divers are filled with air diluted with helium. In bracket 11.7% helium, 56.2% nitrogen and 32.1% oxygen. At high altitudes, the partial pressure of oxygen is less than that at the ground level. This leads to low concentration of oxygen in the blood and tissues of people living at high altitudes or climbers. Low blood oxygen causes climbers to become weak and unable to think clearly. Symptoms of a condition known as anoxia. Effect of temperature. Solubility of gases in liquids decreases with rise in temperature. When dissolved, the gas molecules are present in liquid phase and the process of dissolution can be considered similar to condensation, and heat is evolved in this process. We have learnt in the last section that dissolution process involves dynamic equilibrium and thus must follow Le Chatelier's principle. As dissolution is an exothermic process, the solubility should decrease with increase of temperature. Vapor pressure of liquid solutions. Liquid solutions are formed when solvent is a liquid. The solute can be a gas, a liquid, or a solid. Solutions of gases in liquids have already been discussed in section 2.3.2. In this section, we shall discuss the solutions of liquids and solids in a liquid. Such solutions may contain one or more volatile components. Generally, the liquid solvent is volatile. The solute may or may not be volatile. We shall discuss the properties of only binary solutions, that is, the solution containing two components, namely the solutions of first liquids in liquids and second solids in liquids. 2.4.1 Vapor pressure of liquid solutions. Let us consider a binary solution of two volatile liquids and denote the two components as 1 and 2. When taken in closed vessel, both the components would evaporate and eventually an equilibrium would be established between vapor phase and the liquid phase. Let the total vapor pressure at this stage be P total and P1 and P2 be the partial vapor pressures of the two components 1 and 2 respectively. These partial pressure are related to the mole fractions x1 and x2 of the two components 1 and 2 respectively. The French chemist Francois-Martin Raoult in bracket 1886 gave the quantitative relationship between them. The relationship is known as the Raoult's law, which states that for a solution of volatile liquids, the partial vapor pressure of each component of the solution is directly proportional to its mole fraction present in solution. Thus, for component 1, P1 is directly proportional to x1 and P1 is equals to P01 into x1, where P01 is the vapor pressure of pure component 1 at the same temperature. Similarly, for component 2, P2 is equals to P02 into X2, where P02 represents the vapor pressure of the pure component 2. According to Dalton's law of partial pressures, the total pressure in bracket P total over the solution phase in the container will be the same of the partial pressure of the components of the solution and is given as P total is equals to P1 plus P2. Substituting the values of P1 and P2, we get P total is equals to X1 into P01 plus X2 into P02 is equals to, in bracket 1 minus X2 P01 plus X2 into P02 is equals to P01 plus, in bracket, P02 minus P01 into X2. Following conclusions can be drawn from equation 2.16. First, total vapor pressure over the solution can be related to the mole fraction of any one component. Second, total vapor pressure over the solution varies linearly with the mole fraction of component 2. And third, depending on the vapor pressures of the pure components 1 and 2, total vapor pressure over the solution decreases or increases with the increase of the mole fraction of component 1. A plot of P1 and P2 versus the mole fractions X1 and X2 for a solution gives a linear plot as shown in figure 2.3. These lines in bracket 1 and 2 pass through the points for which X1 and X2 are equal to unity. Similarly, the plot in bracket line 3 of P total versus X2 is also linear in bracket figure 2.3. The minimum value of P total is P01 and the maximum value is P02, assuming that component 1 is less volatile than component 2, that is P01 less than P02. The composition of vapor phase in equilibrium with the solution is determined by the partial pressures of the components. If Y1 and Y2 are the mole fractions of the components 1 and 2 respectively in the vapor phase, then using Dalton's law of partial pressure, P1 is equals to Y1 P total, P2 is equals to Y2 P total. In general, P1 is equals to Y1 into P total. Example 2.5. Vapor pressure of chloroform in bracket CHCl3 and dichloromethane in bracket CH2Cl2 at 298 Kelvin are 200 mm Hg and 415 mm Hg respectively. First, calculate the vapor pressure of the solution prepared by mixing 25.5 gram of CHCl3 and 40 gram of CH2Cl2 at 298 Kelvin, and second, mole fractions of each component in vapor phase. Solution. First, molar mass of CH2Cl2 is equals to 85 gram per mole. Molar mass of CHCl3 is equals to 119.5 gram per mole. Moles of CH2Cl2 is equals to 40 gram upon 85 gram per mole is equals to 0.47 mole. Moles of CHCl3 is equals to 25.5 gram upon 119.5 gram per mole is equals to 0.213 mole. Total number of moles is equal to 0.47 plus 0.213 is equals to 0.683 mole. Mole fraction of CH2Cl2 is equals to 0.47 mole upon 0.683 mole is equals to 0.688. Mole fraction of CHCl3 is equals to 1 minus 0.688 is equals to 0.312. Using equation 2.16, P total is equals to P01 plus in bracket P02 minus P01 into X2 is equals to 200 plus in bracket 415 minus 200 into 0.688 is equals to 200 plus 147.9 is equals to 347.9 mmHg. Second, using the relation in bracket 2.19, Y1 is equals to P1 upon P total, we can calculate the mole fraction of the components in gas phase in bracket Y1. PCH2Cl2 is equals to 0.688 into 415 mmHg is equals to 285.5 mmHg. PCHCl3 is equals to 0.312 into 200 mmHg is equals to 62.4 mmHg. YCH2Cl2 is equals to 285.5 mmHg upon 347.9 mmHg is equals to 0.82. YCH3Cl3 is equals to 62.4 mmHg per 347.9 mmHg is equals to 0.18. Note, since CH2Cl2 is a more volatile component than CHCl3, in bracket P0 CH2Cl2 is equals to 415 mmHg and P0 CHCl3 is equals to 200 mmHg, and the vapor phase is also richer in CH2Cl2. In bracket YCH2Cl2 is equals to 0.82 and YCHCl3 is equals to 0.18. It may thus be concluded that at equilibrium, vapor phase will be always rich in the component which is more volatile. (2.4.2) Raoult's law as a special case of Henry's law. According to Raoult's law, the vapor pressure of a volatile component in a given solution is given by P1 is equals to x1 into P01. In the solution of a gas in a liquid, one of the components is so volatile that it exists as a gas, and we have already seen that its solubility is given by Henry's law, which states that P is equals to Henry constant into X. If we compare the equations for Raoult's law and Henry's law, it can be seen that the partial pressure of the volatile component or a gas is directly proportional to its mole fraction in solution. Only the proportionality constant, Henry constant, differs from P01. Thus, Raoult's law becomes a special case of Henry's law in which Henry constant becomes equal to P01. 2.4.3 Vapor pressure of solutions of solids in liquids. Another important class of solutions consists of solids dissolved in liquid, for example sodium chloride, glucose, urea and cane sugar in water and iodine, and sulfur dissolved in carbon disulfide. Some physical properties of these solutions are quite different from those of pure solvents. For example, vapor pressure. We have learnt in Unit 5, Class 11 that liquids at a given temperature vaporize, and under equilibrium conditions, the pressure exerted by the vapors of the liquid over the liquid phase is called vapor pressure. In bracket figure 2.4a. In a pure liquid, the entire surface is occupied by the molecules of the liquid. If non-volatile solute is added to a solvent to give a solution, in bracket figure 2.4b, the vapor pressure of the solution is solely from the solvent alone. This vapor pressure of the solution at a given temperature is found to be lower than the vapor pressure of the pure solvent at the same temperature. In the solution, the surface has both solute and solvent molecules. Thereby, the fraction of the surface covered by the solvent molecules get reduced. Consequently, the number of solvent molecules escaping from the surface is correspondingly reduced. Thus, the vapor pressure is also reduced. The decrease in the vapor pressure of solvents depends on the quantity of non-volatile solute present in the solution, irrespective of its nature. For example, decrease in the vapor pressure of water by adding 1.0 mole of sucrose to 1 kilogram of water is nearly similar to that produced by adding 1 mole of urea to the same quantity of water at the same temperature. Raoult's law in its general form can be stated as, for any solution, the partial vapor pressure of each volatile component in the solution is directly proportional to its mole fraction. In a binary solution, let us denote the solvent by 1 and solute by 2. When the solute is non-volatile, only the solvent molecules are present in vapor phase and contribute to vapor pressure. Let P1 be the vapor pressure of the solvent. X1 be its mole fraction, P01 be its vapor pressure in the pure state. Then according to Raoult's law, P1 is directly proportional with X1 and P1 is equals to X1 into P01. The proportionality constant is equal to the vapor pressure of pure solvent, P01. A plot between the vapor pressure and the mole fraction of the solvent is linear. In bracket figure 2.5. 2.5. Ideal and non-ideal solutions. Liquid-liquid solutions can be classified into ideal and non-ideal solutions on the basis of Raoult's law. 2.5.1. Ideal solutions. The solutions which obey Raoult's law over the entire range of concentration are known as ideal solutions. The ideal solutions have two other important properties. The enthalpy of mixing of the pure components to form the solution is 0 and the volume of mixing is also 0. That is, delta mix H is equals to 0, delta mix V is equals to 0. It means that no heat is absorbed or evolved when the components are mixed. Also, the volume of solution would be equal to the sum of volumes of the two components. At molecular level, ideal behavior of the solutions can be explained by considering two components A and B. In pure components, the intermolecular attractive interactions will be of types AA and BB. Whereas in the binary solutions, in addition to this, two interactions, AB type of interactions will also be present. If the intermolecular attractive forces between the AA and BB are nearly equal to those between AB, this leads to the formation of ideal solution. A perfectly ideal solution is rare, but some solutions are nearly ideal in behavior. Solution of N-hexane and N-heptane, bromoethane and chloroethane, benzene and toluene, etc. fall into this category. (2.5.2) Non-ideal solutions. When a solution does not obey Raoult's law over the entire range of concentration, then it is called non-ideal solution. The vapor pressure of such a solution is either higher or lower than that predicted by Raoult's law. In bracket equation 2.16. If it is higher, the solution exhibits positive deviation, and if it is lower, it exhibits negative deviation from Raoult's law. The plots of vapor pressure as a function of mole fractions for such solutions are shown in figure 2.6. The cause for these deviations lie in the nature of interactions at the molecular level. In case of positive deviation from Raoult's law, AB interactions are weaker than those between AA or BB. That is, in this case, the intermolecular attractive forces between the solute-solvent molecules are weaker than those between the solute and solvent-solvent molecules. This means that in such solutions, molecules of A or B will find it easier to escape than in pure state. This will increase the vapor pressure and result in positive deviation. Mixtures of ethanol and acetone behave in this manner. In pure ethanol, molecules are hydrogen bonded. On adding acetone, its molecules get in between the host molecules and break some of the hydrogen bonds between them. Due to weakening of interactions, the solutions show positive deviations from Raoult's law. In bracket figure 2.6a. In a solution formed by adding carbon disulfide to acetone, the dipolar interaction between solute-solvent molecules are weaker than the respective interactions among the solute-solute and solvent-solvent molecules. This solution also shows positive deviation. In case of negative deviations from Raoult's law, the intermolecular attractive forces between AA and BB are weaker than those between AB and leads to decrease in vapor pressure resulting in negative deviations. An example of this type is a mixture of phenol and aniline. In this case, the intermolecular hydrogen bonding between phenolic proton and lone pair on nitrogen atom of aniline is stronger than the respective intermolecular hydrogen bonding between similar molecules. Similarly, a mixture of chloroform and acetone forms a solution with negative deviation from Raoult's law. This is because chloroform molecule is able to form hydrogen bond with acetone molecule as shown. This decreases the escaping tendency of molecules for each component and consequently the vapor pressure decreases resulting in negative deviation from Raoult's law. In bracket figure 2.6b. Some liquids on mixing form azeotropes, which are binary mixtures having the same composition in liquid and vapor phase and boil at a constant temperature. In such cases, it is not possible to separate the components by fractional distillation. There are two types of azeotropes called minimum boiling azeotrope and maximum boiling azeotrope. The solutions which show a large positive deviation from Raoult's law form minimum boiling azeotrope at a specific composition. For example, ethanol water mixture in bracket obtained by fermentation of sugars on fractional distillation gives a solution containing approximately 95% by volume of ethanol. Once this composition, known as azeotrope composition, has been achieved, the liquid and vapor have the same composition and no further separation occurs. The solutions that show large negative deviation from Raoult's law form maximum boiling azeotrope at a specific composition. Nitric acid and water is an example of this class of azeotrope. This azeotrope has the approximate composition 68% nitric acid and 32% water by mass, with a boiling point of 393.5 Kelvin. (2.6) Colligative properties and determination of molar mass. We have learnt in section 2.4.3 that the vapor pressure of solution decreases when a non-volatile solute is added to a volatile solvent. There are many properties of solutions which are connected with this decrease of vapor pressure. These are: first, relatively lowering of vapor pressure of the solvent. Second, depression of freezing point of the solvent. Third, elevation of boiling point of the solvent. And fourth, osmotic pressure of the solution. All these properties depend on the number of solute particles irrespective of the nature relative to the total number of particles present in the solution. Such properties are called colligative properties. In bracket, colligative from Latin, co means together, ligare means to bind. In the following sections, we will discuss these properties one by one. 2.6.1 Relative lowering of vapor pressure. We have learnt in section 2.4.3 that the vapor pressure of a solvent in solution is less than that of the pure solvent. Raoult established that the lowering of vapor pressure depends only on the concentration of the solute particles and it is independent of their identity. The equation in bracket 2.20 given in section 2.4.3 establishes a relation between vapor pressure of the solution, mole fraction, and vapor pressure of the solvent. That is, P1 is equals to X1 into P01. The reduction in the vapor pressure of solvent in bracket delta P1 is given as delta P1 is equals to P01 minus P1 is equals to P01 minus P01 into X1 is equals to P01 in bracket 1 minus X1. Knowing that X2 is equals to 1 minus X1, equation 2.23 reduces to delta P1 is equals to X2 into P01. In a solution containing several non-volatile solutes, the lowering of the vapor pressure depends on the sum of the mole fraction of different solutes. In a solution containing several non-volatile solutes, the lowering of the vapor pressure depends on the sum of the mole fraction of different solutes. Equation 2.24 can be written as delta P1 upon P01 is equals to P01 minus P1 upon P01 is equals to X2. The expression on the left-hand side of the equation as mentioned earlier is called relatively lowering of vapor pressure and is equal to the mole fraction of the solute. The above equation can be written as P01 minus P1 upon P01 is equals to N2 upon N1 plus N2 in bracket since X2 is equals to N2 upon N1 plus N2. Here N1 and N2 are the number of moles of solvent and solute respectively present in the solution. For dilute solutions, N2 is very less than the N1. Hence, neglecting N2 in the denominator, we have P01 minus P1 upon P01 is equals to N2 upon N1. Or P01 minus P1 upon P01 is equals to W2 into M1 upon M2 into W1. Here W1 and W2 are the masses and M1 and M2 are the molar masses of the solvent and solute respectively. From this equation 2.28, knowing all other quantities, the molar mass of solute in bracket M2 can be calculated. Example 2.6. The vapor pressure of pure benzene at a certain temperature is 0.850 bar. A non-volatile, non-electrolyte solid weighing 0.5 gram when added to 39 gram of benzene in bracket molar mass 78 gram per mole. Vapor pressure of the solution then is 0.845 bar. What is the molar mass of the solid substance? Solution. The various quantities known to us are as follows. P01 is equals to 0.850 bar, P is equals to 0.845 bar, M1 is equals to 78 gram per mole, W2 is equals to 0.5 gram, W1 is equals to 39 gram. Substituting these values in equation 2.28, we get 0.850 bar minus 0.845 bar upon 0.850 bar is equals to 0.5 gram into 78 gram per mole upon M2 into 39 gram. Therefore, M2 is equals to 170 gram per mole. 2.6.2 Elevation of boiling point. We have learnt in Unit 5, Class 11 that the vapor pressure of a liquid increases with increase of temperature. It boils at the temperature at which its vapor pressure is equal to the atmospheric pressure. For example, water boils at 373.15 Kelvin in bracket 100 degrees Celsius because at this temperature the vapor pressure of water is 1.013 bar in bracket 1 atmosphere. We have also learnt in the last section that vapor pressure of the solvent decreases in the presence of non-volatile solute. Figure 2.7 depicts the variation of vapor pressure of the pure solvent in solution as a function of temperature. For example, the vapor pressure of an aqueous solution of sucrose is less than 1.013 bar at 373.15 Kelvin. In order to make this solution boil, its vapor pressure must be increased to 1.013 bar by raising the temperature above the boiling temperature of the pure solvent that is water in bracket water. Thus, the boiling point of a solution is always higher than that of the boiling point of the pure solvent in which the solution is prepared as shown in figure 2.7. Similar to lowering of vapor pressure, the elevation of boiling point also depends on the number of solute molecules rather than their nature. A solution of 1 mole of sucrose in 1000 gram of water boils at 373.52 Kelvin at 1 atmospheric pressure. Let T0 be the boiling point of pure solvent and Tb be the boiling point of solution. The increase in the boiling point delta Tb is equals to Tb minus T0b is known as elevation of boiling point. Experiments have shown that for dilute solutions, the elevation of boiling point in bracket delta Tb is directly proportional to the molar concentration of the solute in a solution. Thus, delta Tb is directly proportional with molar concentration or delta Tb is equals to Kb into m. Here M Molality is the number of moles of solute dissolved in 1 kg of solvent, and the constant of proportionality Kb is called boiling point elevation constant or molar elevation constant, in bracket ebullioscopic constant. The unit of Kb is Kelvin into kg per mole. Values of Kb for some common solvents are given in table 2.3. If W2 gram of solute of molar mass M2 is dissolved in W1 gram of solvent, then molality M of the solution is given by the expression M is equals to W2 upon M2 upon W1 upon 1000 into 1000 into W2 upon M2 into W1. Substituting the value of molality in equation 2.30, we get delta Tb is equals to Kb into 1000 into W2 upon M2 into W1. M2 is equals to 1000 into W2 into Kb upon delta Tb into W1. Thus, in order to determine M2, molar mass of the solute, known mass of solute in a known mass of the solvent is taken, and delta Tb is determined experimentally for a known solvent whose Kb value is known. Example 2.7, 18 gram of glucose 6C6H12O6 is dissolved in 1 kg of water in a saucepan. At what temperature will water boil at 1.013 bar? Kb for water is 0.52 Kelvin kg per mole. Moles of glucose is equals to 18 gram upon 180 gram per mole is equals to 0.1 mole. Numbers of kilograms of solvent is equals to 1 kg. Thus, molality of glucose solution is equals to 0.1 mole per kg. For water change in boiling point, delta Tb is equals to Kb into M is equals to 0.52 Kelvin into kg per mole into 0.1 mole per kg is equals to 0.052 Kelvin. Since water boils at 373.15 Kelvin at 1.013 bar pressure, therefore the boiling point of solution will be 373.15 plus 0.052 is equals to 373.202 Kelvin. Example 2.8. The boiling point of benzene is 353.23 Kelvin. When 1.80 gram of a non-volatile solute was dissolved in 90 gram of benzene, the BP is raised to 354.11 Kelvin. Calculate the molar mass of the solute. Kb for benzene is 2.53 Kelvin into kg per mole. Solution. The elevation in bracket delta Tb in the boiling point is equals to 354.11 Kelvin minus 353.23 Kelvin is equals to 0.88 Kelvin. Substituting these values in expression 2.33, we get M2 is equals to 2.53 Kelvin into kg per mole into 1.8 gram into 1000 gram per kg upon 0.88 Kelvin into 90 gram is equals to 58 gram per mole. Therefore, molar mass of the solute M2 is equals to 58 gram per mole. 2.6.3 Depression of freezing point. The lowering of vapor pressure of a solution causes a lowering of the freezing point compared to that of a pure solvent in bracket figure 2.8. We know that at the freezing point of a substance, the solid phase is in dynamic equilibrium with the liquid phase. Thus, the freezing point of a substance may be defined as the temperature at which the vapor pressure of the substance in its liquid phase is equal to its vapor pressure in the solid phase. A solution will freeze when its vapor pressure equals the vapor pressure of the pure solid solvent, as is clear from figure 2.8. According to Raoult's law, when a non-volatile solid is added to the solvent, its vapor pressure decreases and now it would become equal to that of solid solvent at lower temperature. Thus, the freezing point of the solvent decreases. Let T0F be the freezing point of pure solvent and Tf be its freezing point when non-volatile solute is dissolved in it. The decrease in freezing point delta Tf is equals to T0F minus Tf is known as depression in freezing point. Similar to elevation of boiling point, depression of freezing point in bracket delta Tf for dilute solution in bracket ideal solution is directly proportional to molarity M of the solution. Not molarity, it is molality. Thus, delta Tf is directly proportional with molality, or delta Tf is equals to Kf into M. The proportionality constant Kf, which depends on the nature of the solvent, is known as freezing point depression constant or molar depression constant or cryoscopic constant. The unit of Kf is Kelvin kg per mole. Values of Kf for some common solvents are listed in table 2.3. If W2 gram of the solute having molar mass as M2 present in W1 gram of solvent produces the depression in freezing point delta Tf of the solvent, then molality of the solute is given by the equation 2.31. Molarity is equals to, not molarity, again molality is equals to W2 upon M2 upon W1 upon 1000. Substituting this value of molality in equation 2.34, we get delta Tf is equals to Kf into W2 upon M2 upon W1 upon 1000. Delta Tf is equals to Kf into W2 into 1000 upon M2 into W1. M2 is equals to Kf into W2 into 1000 upon delta Tf into W1. Thus, for determining the molar mass of the solute, we should know the quantities W1, W2, delta Tf along with the molar freezing point depression constant. The values of Kf and Kb, which depend upon the nature of the solvent, can be ascertained from the following relations. The values of Kf and Kb, which depend upon the nature of the solvent, can be ascertained from the following relations. Kf is equals to R into M1 into T square F upon 1000 into delta fusion H. Kb is equals to R into M1 into T square B upon 1000 into delta vaporization H. Here the symbols R and M1 stand for the gas constant and molar mass of the solvent respectively, and Tf and Tb denote the freezing point and the boiling point of the pure solvent respectively in Kelvin. Further, delta fusion enthalpy and delta vaporization enthalpy represent the enthalpies for the fusion and vaporization of the solvent respectively. Example 2.9. 45 gram of ethylene glycol C2H6O2 in bracket is mixed with 600 gram of water. Calculate A, the freezing point depression, and B, the freezing point of the solution. Solution: depression in freezing point is related to the molality. Therefore, the molality of the solution with respect to ethylene glycol is equals to moles of ethylene glycol upon mass of water in kilogram. Moles of ethylene glycol is equals to 45 gram upon 62 gram per mole is equals to 0.73 mole. Mass of water in kg is equals to 600 gram upon 1000 gram per kg is equals to 0.6 kg. Hence, molality of ethylene glycol is equals to 0.73 mole per 0.60 kg is equals to 1.2 mole per kg. Therefore, freezing point depression is equals to 1.86 Kelvin kg per mole into 1.2 mole per kg is equals to 2.2 Kelvin. Freezing point of the aqueous solution is equals to 273.15 Kelvin minus 2.2 Kelvin is equals to 270.95 Kelvin. Example 2.10. 1 gram of a non-electrolyte solute dissolved in 50 gram of benzene lowered the freezing point of benzene by 0.40 Kelvin. The freezing point depression constant of benzene is 5.12 Kelvin kg per mole. Find the molar mass of the solute. Solution. Substituting the values of various terms involved in equation 2.36, we get M2 is equals to 5.12 Kelvin into kg per mole into 1 gram into 1000 gram per kg upon 0.40 into 50 gram is equals to 256 gram per mole. Thus, molar mass of the solute is equals to 256 gram per mole. 2.6.4 Osmosis and osmotic pressure. There are many phenomena which we observe in nature or at home. For example, raw mangoes shrivel when pickled in brine in briquette salt water. Wilted flowers revive when placed in fresh water. Blood cells collapse when suspended in saline water, etc. If we look into these processes, we find one thing common in all. That is, all these substances are bound by membranes. These membranes can be of animal or vegetable origin, and this occur naturally, such as pig's bladder or parchment, or can be synthetic such as cellophane. These membranes appear to be continuous sheets or films, yet they contain a network of submicroscopic holes or pores. Small solvent molecules like water can pass through these holes, but the passage of bigger molecules like solute is hindered. Membranes having this kind of properties are known as semi-permeable membranes. In bracket SPM. Assume that only solvent molecule can pass through these semi-permeable membranes. If this membrane is placed between the solvent and solution as shown in figure 2.9, the solvent molecules will flow through the membrane from pure solvent to the solution. This process of flow of the solvent is called osmosis. The flow will continue till the equilibrium is attained. The flow of the solvent from its side to solution side across a semi-permeable membrane can be stopped if some extra pressure is applied on the solution. This pressure that just stops the flow of solvent is called osmotic pressure of the solution. The flow of solvent from dilute solution to the concentrated solution across a semi-permeable membrane is due to osmosis. The important point to be kept in mind is that solvent molecules always flow from lower concentration to higher concentration of solution. The osmotic pressure has been found to depend on the concentration of the solution. The osmotic pressure of a solution is the excess pressure that must be applied to a solution to prevent osmosis. That is, to stop the passage to solvent molecules through a semi-permeable membrane into the solution. This is illustrated in figure 2.10. Osmotic pressure is a colligative property as it depends on the number of solute molecules and not on their identity. For dilute solutions, it has been found experimentally that osmotic pressure is proportional to the molarity C of the solution at a given temperature T. Thus, pi is equals to CRT. Here pi is the osmotic pressure and R is the gas constant. Pi is equals to N2 upon V into RT. Here V is volume of a solution in liters containing N2 moles of solute. If W2 grams of solute of molar mass M2 is present in the solution, then N2 is equals to W2 upon M2, and we can write pi into V is equals to W2 into RT upon M2, or M2 is equals to WRT upon pi V. Thus, knowing the quantities W2, T, pi and V, we can calculate the molar mass of the solute. Measurement of osmotic pressure provides another method of determining molar masses of solutes. This method is widely used to determine molar masses of proteins, polymers, and other macromolecules. The osmotic pressure method has the advantage over other methods as pressure measurement is around the room temperature and the molarity of the solution is used instead of molality. As compared to other colligative properties, its magnitude is large even for very dilute solutions. The technique of osmotic pressure for determination of molar mass of solutes is particularly useful for biomolecules as they are generally not stable at higher temperatures and polymers have poor solubility. Two solutions having same osmotic pressure at a given temperature are called isotonic solutions. When such solutions are separated by semi-permeable membrane, no osmosis occurs between them. For example, the osmotic pressure associated with the fluid inside the blood cell is equivalent to that of 0.9% in bracket mass per volume sodium chloride solution called normal saline solution, and it is safe to inject intravenously. On the other hand, if we place the cells in a solution containing more than 0.9% mass per volume sodium chloride, water will flow out of the cells and they would shrink. Such a solution is called hypertonic. If the salt concentration is less than 0.9% mass per volume, the solution is said to be hypotonic. In this case, water will flow into the cells if placed in this solution and they would swell. Example 2.11. 200 cubic centimeter of an aqueous solution of a protein contains 1.26 gram of the protein. The osmotic pressure of such a solution at 300 Kelvin is found to be 2.57 into 10 to minus 3 bar. Calculate the molar mass of the protein. Solution. The various quantities known to us are as follows. Pi is equals to 2.57 into 10 to minus 3 bar. V is equals to 200 cubic centimeter is equals to 0.200 liter. T is equals to 300 Kelvin. R is equals to 0.083 liter bar per mole into Kelvin. Substituting these values in equation 2.42, we get M2 is equals to 1.26 gram into 0.083 liter into bar upon Kelvin into mole into 300 Kelvin upon 2.57 into 10 to minus 3 bar is into 0.200 liter is equals to 61,022 gram per mole. 61,022 gram per mole. The phenomena mentioned in the beginning of this section can be explained on the basis of osmosis. A raw mango placed in concentrated salt solution loses water via osmosis and shrivel into pickle. Wilted flowers revive when placed in fresh water. A carrot that has become limp because of water loss into the atmosphere can be placed into the water, making it firm once again. Water will move into itself through osmosis. When placed in water containing less than 0.9% mass per volume salt, blood cells swell due to flow of water in them by osmosis. People taking a lot of salt or salty food experience water retention in tissue cells and intercellular spaces because of osmosis. The resulting puffiness or swelling is called edema. Water movement from soil into plant roots or subsequently into upper portion of the plant is partly due to osmosis. The preservation of meat by salting and of fruits by adding sugar protects against bacterial action. Through the process of osmosis, a bacterium on salted meat or candied fruit loses water, shrivels and dies. (2.6.5) Reverse osmosis and water purification. The direction of osmosis can be reversed if a pressure larger than the osmotic pressure is applied to the solution site. That is, now the pure solvent flows out of the solution through the semi-permeable membrane. This phenomenon is called reverse osmosis and is of great practical utility. Reverse osmosis is used in desalination of seawater. A schematic setup for the process is shown in figure 2.11 when pressure more than osmotic pressure is applied. Pure water is squeezed out of the seawater through the membrane. A variety of polymer membranes are available for this purpose. The pressure required for the reverse osmosis is quite high. A workable porous membrane is film of cellulose acetate placed over a suitable support. Cellulose acetate is permeable to water but impermeable to impurities and ions present in seawater. These days, many countries use desalination plants to meet their potable water requirements. 2.7 abnormal molar masses. We know that ionic compounds when dissolved in water dissociate into cations and anions. For example, if we dissolve 1 mole of KCl in bracket 74.5 gram in water, we expect 1 mole each of K plus and Cl minus ions to be released in the solution. If this happens, there would be 2 moles of particles in the solution. If we ignore interionic attractions, 1 mole of KCl in 1 kg of water would be expected to increase the boiling point by 2 into 0.52 Kelvin is equals to 1.04 Kelvin. Now, if we did not know about the degree of dissociation, we could be led to conclude that the mass of 2 mole particles in 74.5 gram and the mass of 1 mole of KCl would be 37.25 gram. This brings into light the rule that when there is dissociation of solute into ions, the experimentally determined molar mass is always lower than the true value. 2CH3COOH gives CH3COOH whole twice. Molecules of ethanoic acid in bracket acetic acid dimerize in benzene due to hydrogen bonding. This normally happens in solvents of low dielectric constant. In this case, the number of particles is reduced due to dimerization. Association of molecules is depicted as follows. It can be undoubtedly stated here that if all the molecules of ethanoic acid associate in benzene, then del TB or del TF for ethanoic acid will be half of the normal value. The molar mass calculated on the basis of this del TB or del TF will therefore be twice the expected value. Such a molar mass that is either lower or higher than the expected or normal value is called as abnormal molar mass. In 1880, Van 't Hoff introduced a factor I known as the Van 't Hoff factor to account for the extent of dissociation or association. This factor I is defined as Van 't Hoff factor is equals to normal molar mass upon abnormal molar mass is equals to observed colligative property upon calculated colligative property. I is equals to total number of moles of particles after association or dissociation upon number of moles of particles before association or dissociation. Here, abnormal molar mass is the experimentally determined molar mass and calculated colligative properties are obtained by assuming that the non-volatile solute is neither associated nor dissociated. In case of association, value of Van 't Hoff factor is less than unity, while for dissociation it is greater than unity. For example, the value of Van 't Hoff factor for aqueous KCl solution is close to 2, while the value for ethanoic acid in benzene is nearly 0.5. Inclusion of Van 't Hoff factor modifies the equations for colligative properties as follows. Relative lowering of vapor pressure of solvent P01 minus P1 upon P01 is equals to Van 't Hoff factor into N2 upon N1. Elevation of boiling point del TB is equals to I into Kb into N. Depression of freezing point del TF is equals to I into Kf into N. Osmotic pressure of solution pi is equals to I into N2 into RT upon V. Table 2.4 depicts values of the factor Van 't Hoff factor for several strong electrolytes. For KCl, NaCl and MgSO4, Van 't Hoff factor values approach 2 as the solution becomes very dilute. As expected, the values of I gets close to 3 for K2SO4. Example 2.12, 2 gram of benzoic acid in bracket C6H5COOH dissolved in 25 gram of benzene shows a depression in freezing point equal to 1.62 Kelvin. Molar depression constant for benzene is 4.9 Kelvin kg per mole. What is the percentage association of acid if it forms dimer in solution? So the given quantities are W2 is equals to 2 gram, Kf is equals to 4.9 Kelvin kg per mole. W1 is equals to 25 gram. Del Tf is equals to 1.62 Kelvin. Substituting these values in equation 2.36, we get M2 is equals to 4.9 Kelvin kg per mole into 2 gram into 1000 gram per kg upon 25 gram into 1.62 Kelvin is equals to 241.98 gram per mole. Thus, experimental molar mass of benzoic acid in benzene is equal to 241.98 gram per mole. Now consider the following equilibrium for the acid. 2C6H5COOH gives C6H5COOH whole twice. If X represents the degree of association of the solute, then we would have 1 minus X mole of benzoic acid left in unassociated form and correspondingly X by 2 as associated moles of benzoic acid at equilibrium. Therefore, total number of moles of particles at equilibrium is 1 minus X plus X by 2 is equals to 1 minus X by 2. Thus, total number of moles of particles at equilibrium equals Volta factor I, but I is equals to abnormal molar mass upon, I is equals to normal molar mass upon abnormal molar mass is equals to 122 gram per mole upon 241.98 gram per mole, or X by 2 is equals to 1 minus 122 upon 241.98 is equals to 1 minus 0.504 is equals to 0.496, or X is equals to 2 into 0.496 is equals to 0.992. Therefore, degree of association of benzoic acid in benzene is 99.2%. Example 2.13. 0.6 ml of acetic acid in bracket CH3COOH having density 1.06 gram per ml is dissolved in 1 liter of water. The depression in freezing point observed for the strength of acid was 0.0205 degrees Celsius. Calculate the Volta factor and the dissociation constant of acid. Solution: number of moles of acetic acid is equals to 0.6 ml into 1.06 gram per ml upon 60 gram per mole is equals to 0.01106 mole is equals to N. Molality is equals to 0.0106 mole per 1000 ml into 1 gram per ml is equals to 0.0106 mole per kg. Using equation 2.35, del Tf is equals to 1.86 Kelvin kg per mole into 0.0106 mole per kg is equals to 0.0197 Kelvin. Volta factor I is equals to observed freezing point upon calculated freezing point is equals to 0.0205 Kelvin upon 0.0197 Kelvin is equals to 1.041. Acetic acid is a weak electrolyte and will dissociate into two ions, acetate and hydrogen ions per molecule of acetic acid. If X is the degree of dissociation of acetic acid, then we would have N in bracket 1 minus X moles of undissociated acetic acid, NX mole of CH3COO minus and NX moles of H plus ions. CH3COOH gives H plus ion plus CH3COO negative ion. Initial concentration will be N mole, and for H plus and CH3COO minus would be 0,0. At equilibrium, the concentration will be N 1 minus X, and for H plus and CH3COO minus it will be NX mole and NX mole. Thus, total moles of particles are N in bracket 1 minus X plus X plus X is equals to N in bracket 1 plus X. Volta factor is equals to N 1 plus X upon N is equals to 1 plus X is equals to 1.041. Thus, degree of dissociation of acetic acid is equals to X is equals to 0.041 minus 1 is equals to 0.041. Then CH3COOH is equals to N in bracket 1 minus X is equals to 0.0106 in bracket 1 minus 0.041. CH3COO minus is equals to NX is equals to 0.0106 into 0.041, comma, H plus ion concentration is equals to NX is equals to 0.0106 into 0.041. Acid constant is equals to CH3COO minus into H plus upon CH3COOH is equals to 0.0106 into 0.041 into 0.0106 into 0.041 upon 0.0106 in bracket 1 minus 0.041 is equals to 1.86 into 10 raised to minus 5. Summary: a solution is a homogeneous mixture of two or more substances. Solutions are classified as solid, liquid and gaseous solutions. The concentration of solution is expressed in terms of mole fraction, molarity, molality and in percentage. The dissolution of a gas in a liquid is governed by Henry's law, according to which at a given temperature, the solubility of a gas in a liquid is directly proportional to the partial pressure of the gas. The vapor pressure of the solvent is lowered by the presence of a non-volatile solute in the solution, and this lowering the vapor pressure of the solvent is governed by Raoult's law, according to which the relative lowering of vapor pressure of the solvent over a solution is equal to the mole fraction of a non-volatile solute present in the solution. However, in a binary liquid solution, if both the components of the solution are volatile, then another form of Raoult's law is used. Mathematically, this form of the Raoult's law is stated as P total is equals to P01 into x1 plus P02 into x2. Solutions which obey Raoult's law over the entire range of concentration are called ideal solutions. Two types of deviations from Raoult's law called positive and negative. Deviations are observed. Azeotropes arise due to very large deviations from Raoult's law. The properties of solutions which depend on the number of solid particles and are independent of their chemical identity are called colligative properties. These are lowering of vapor pressure, elevation of boiling point, depression in freezing point and osmotic pressure. The process of osmosis can be reversed if a pressure higher than the osmotic pressure is applied to the solution. Colligative properties have been used to determine the molar mass of solutes. Solutes which dissociate in solution exhibit molar mass lower than the actual molar mass, and those which associate show higher molar mass than their actual values. Quantitatively, the extent to which a solute is dissociated or associated can be expressed by Volta factor I. This factor has been defined as ratio of normal molar mass to experimentally determined molar mass, or as the ratio of observed colligative property to the calculated colligative property.